Today, we're going to look at trigonometric identities. But before we start, a small announcement. On my website, under handouts, I put together a solving triangles worksheets. You'll be able to find it if you go to the website and look under handouts. There's not much there. It is not a formal homework assignment. I will put an answer key up in a few days. But for those of you who are not feeling 100% about solving triangles, it would behoove you to go through it, solve these triangles, check your answers. If you have difficulty working with your classmates, come to office hours, tutoring, whatever. Most assuredly, solving triangles will be on the final, so you want to feel comfortable and put snuff on that. Okay. So, let's talk about identities. We already have one identity that we've run into. Sine squared x plus cosine squared x equals 1. This is a statement which is true for all x. There might be, here there are two expressions, but one of them is kind of simple. It's just 1. But you might have two more complicated expressions. And we think of identities as being theorems. In other words, you could restate this as, for all x, sine squared of x plus cosine squared of x equals 1. But we think of them as an if and only theorem. That is, this side implies this side, and this side implies this side. So when we take one of these expressions, we want to prove that it's really an identity. There are really two proofs involved. However, you'll see that there's a shortcut we can use most of the time. All right, so first, just an example of an identity which is not really a trigonometric identity. But if I were to say x plus x minus 6 equals 4x minus 12 over 2. And I say, well, okay, I believe this is an identity, but I want to prove it. I want to show that this is true for all x, and that if I assume this side, I can show this side is true, and vice versa. And as a proof, I want my steps either to be transparently obvious what I'm doing, so that anyone reading it would go, aha, that was valid. Or I might want to state what I'm doing. We'll probably do more of the former in this class, but all right. So I'm going to start on one side, and I'm going to say, all right, x plus x, that's 2x minus 6. It's just rules of algebra. And I could take this expression I can multiply it by 2 over 2. 2 over 2 is a name for 1, so I'm really just using the identity property of multiplication. And then I could distribute, and I'd get 4x minus 12 over 2. And so the first part of my proof would be complete. I've shown that x plus x minus 6 implies 4x minus 12 over 2. The second part of the proof would be I would start on this side and work my way back. But as I said, there's a very simple shortcut I can usually apply, which is I can just state that all my steps here were reversible. If all my steps are reversible, then I can just as easily go through this proof backwards, right? Whether it's here, I'm factoring out a factor of 2, right? I'm reverse distributing, and so forth. So it's usually not necessary to, show the equivalence in both directions. We're gonna look at and do prove some identities, but first we want to build up kind of a textbook of identities or theorems that we can use in proving them. We've run across most of these already, so there'll be a little review here. Let's start with some statements which, well, let's just start with tangent of x equals sine of x over cosine of x. If you start with the triangle definition of tangent, sine, and cosine, then this is actually an identity, a theorem. But if you use the circle definition, this is really a definition. So there's a little looseness here, but it doesn't matter, definition or identity, this is really useful, and we can use it in our proofs. Similarly, we know that the cotangent of x is the cosine of x over the sine of x. And here we have two statements which really are definitions, but again, we can use them as identities. The cosecant of x is 1 over the sine of x, and the secant of x is 1 over the cosine of x. Okay, so I think the book calls these fundamental or basic identities. Let's try doing a very simple proof. This is so simple as to be trivial, but I'd like to show that the tangent of x equals 1 over cotangent of x. I'm more interested in the mechanics right now, since this should be fairly obvious. So we're going to start on the left side, and using our identity on the left, we're going to change tangent of x to sine of x over cosine of x. And then I'm going to multiply this expression by a form of 1. That is 1 over the sine of x over 1 over sine of x. On the top, I'm going to get sine of x over sine of x, and on the bottom, I'm going to get cosine of x over sine of x. But sine of x over sine of x, that's just a name for 1. So this is 1 over cosine of x over the sine of x. But again, we have an identity that tells us that's the cotangent of x. So here I started on the left side. I I've made valid manipulations here, and I've come up with what's on the right side. Again, that's just the first half of the proof, but in this case, we can see that all these steps here are, of course, reversible. So this is now a valid identity. I'm not going to write that one up. Here, these are my basic identities. All right, now I want to build up, again, a few other groups of identities that you really need to know, kind of like the back of your hand, because they're going to be useful in trying to prove other identities. Let's start with sine squared x plus cosine squared x equals 1. We'll just take that. I think we showed it. That was the case in another class. But I'd like to start with that identity. And I'd like to use it to show the following identity. Tangent squared x plus 1 equals secant squared x. Okay. So one strategy in trying to solve these identities is to convert everything to sines and cosines and see where that leads you. So here I'm going to convert tangent squared x to, well, first of all, that's sine of x over cosine of x squared. And secant squared, of course, is 1 over cosine squared of x. This becomes sine squared x over cosine squared x plus 1. And now I'm going to do something we're also going to do quite commonly. When we have a fraction, we're going to put everything over a common denominator. So this becomes sine squared x plus cosine squared x over cosine squared x. And this is still 1 over cosine squared x. Well, sine squared x plus cosine squared x is, of course, 1. Right? So, I didn't want to do this. I didn't want to do the right side. I just wanted to do the left side. Cosine squared, 1 over cosine squared, of course, is secant squared of x. So, again, my proof is I start with one side, I do manipulations, I find my way over to the other side, and again, in this case, I can recognize that I can reverse these steps, so this is a valid identity. This is tangent squared x plus 1 equals secant squared. In a similar vein, I can find that 1 plus cotangent squared x equals cosecant squared x. Essentially the same process. I can convert these to sines and cosines. I'll have an elimination when sine squared plus cosine squared equals 1, and I'll see this is also true. So these three identities are referred to as the Pythagorean identities because they all branch out of sine squared x plus cosine squared of x, which we show using the Pythagorean theorem. It's useful to know that we can manipulate these a little in ways that we're going to find useful. For example, I could write this as 1 minus sine squared x equals cosine squared x, or 1 minus cosine squared x equals sine squared x. Similarly with these, we could also have tangent squared x equals secant squared x minus 1, and the same with cotangent, secant squared again. All right, this will come up a little later. A lot of material today. If I say something too quickly or confused, you should slow me down, right? If it all makes perfect sense, just let me go. We'll get out early, right? All right. The next set of these are identities, but I'll think of them as tools. Sorry. It's a little neurotic, but yes, it's going. All right. We've seen that the sine of minus x is equal to the minus sine of x, this being an odd function. And the cosine of minus x equals cosine of x, this being an even function. Nice to know these relationships for the other 4 trig functions. So let me start with an unproven identity. Tangent of minus x equals minus tangent of x. In other words, I suspect the tangent is an odd function. So how would I go about showing that? Well, tangent of minus x is, of course, sine of minus x over cosine of minus x. That's one of my basic identities. Sine of minus x is minus sine of x. Cosine of minus x is cosine of x. That's my odd and even identities. And this is, of course, minus tangent of x, which is what I wanted to show. So I can add this to my list. Tangent of minus x equals minus tangent of x. It's also an odd function. Without much effort, I think you can see that the cotangent is going to have the same property. Proof is pretty much the same, except everything here is reciprocal. So last we want to look at secant of minus x. Right? Secant of minus x, well, that's going to be secant of x. This is going to be an even function. Secant of minus x is 1 over the cosine of minus x. But we know the cosine of minus x is just the cosine of x. And that, of course, is secant of x. So this is an even function. And finally, we can do the same operation with the cosecant, but the cosecant being 1 over the sine, and we're going to find this is going to be an odd function. So these are our odd, even identities we can use. All right. There's one more set of identities we're going to look at, fundamental kind of identities. I think we've looked at these before, but we're going to go back to the triangle definition of trig functions. We have a triangle with an angle theta. The right triangle has a hypotenuse, is the side opposite theta and the side adjacent to theta. And we have the sine of theta is the opposite over the hypotenuse, and the cosine of theta is the adjacent over the hypotenuse. But in this diagram, we have a second angle. This is a complementary angle to theta. The sum of these angles all have to add up to 180. So theta plus 90 minus theta plus our right angle is 180. And if I look at the trig functions of these angles, of this angle, I find that the sine of 90 degrees minus theta is what? It's A over H. And the cosine is 90 degrees minus theta is the opposite over H. But of course we can see both of these are equal to O over H, so the cosine of 90 degrees minus theta is the sine of theta. And the sine of 90 degrees minus theta is the cosine of theta. So these are our basic cofunctions called cofunction identities. So sine of 90 minus theta is cosine of theta. Cosine of 90 minus theta is sine of theta. And of course there are four other such relations we can derive just using these identities. If we wanted to know what the tangent of 90 minus theta is, we would convert that to sine of 90 degrees minus theta over cosine 90 degrees minus theta. But that's just the cosine of theta over the sine of theta, which is the cotangent of theta. So tangent of 90 degrees minus theta equals cotangent of theta. By now, you can see that all these names now suddenly are going to line up very nicely, right? Sine, cosine, tangent, cotangent. We want to look at what the secant of 90 degrees minus theta is. That's 1 over the cosine of 90 degrees minus theta, or 1 over the sine of theta, which of course is the cosecant of theta. these also are co-functions. And I'm leaving 2 out. Obviously, the cotangent of 90 minus theta will be the tangent of theta, and the cosecant of 90 minus theta will be the secant of theta. They're all co-functions. Okay, that's a basic set of identities that we're going to use to solve or prove other identities. Let's look at something a little more meaty. Okay? Let's look at the identity cosine of x plus tangent of x, sine of x equals secant of x. Well, let's try that strategy where we convert everything to sines and cosines. Right? Again, it's going to often be very useful. Not always, but so we have the cosine of x plus tangent of x is sine of x over cosine of x times sine of x, which is just cosine of x plus sine squared x over cosine of x. And now I want to try that other strategy, which is when I have a fraction, to put things over a common denominator. So I have to multiply cosine of x times cosine of x over cosine of x. It's just multiplying it by 1. I get cosine squared x plus sine squared x all over cosine of x. But that's cosine squared x plus sine squared x over cosine squared x. We're going to see these Pythagorean identities a lot. They're often going to help us reduce something. Cosine x plus squared x plus sine squared x is just 1, so we have 1 over cosine squared x. I did something wrong. Oh. Not over cosine squared x, just over cosine of x. That's secant of x. Okay, so we start on the left side, we convert everything to sines and cosines, we put it over a common denominator, we try reducing things, and we find we end up where we want to be. And since our steps are reversible, we know this is to be a valid identity. All right. A note, well, a couple notes on doing these. We're trying to prove something is true. You might at some point be asked to prove something is true, and in the process you might find that difficult, and you might begin to suspect that maybe what you're being asked to prove isn't true. Well, it's very, very easy to show that something is not true. You just need one counterexample. So, for example, if I suggested to you that sine of x plus cosine of x equals 1, Well, you might look at that, you might think, it almost sounds plausible. I mean, if I said x equals 0, this becomes 0 plus 1, that's 1. And let's just try something else simple. Let's try 90 degrees. Well, that would be sine of x is 1 plus cosine of 0 is 1. So at least on the surface it might look plausible. But of course this is not true. It's very easy to show that. We just have to pick some other value. We can just go with 180 degrees. Sine of 180 is 0, but the cosine is minus 1. It's definitely not 1. So merely by choosing x equal to 180, we've shown that this is not a trig identity. It's not in general true. Another thing you want to watch out for, you'll notice that when I have an identity, I typically work on one side or the other. But I haven't been just performing some operation on both sides. That operation might be valid, but it would require that it's a reversible operation. So in general, it's best to try and avoid that. As an example, I could start with something like this. I could say sine of minus x equals sine of x. Now, we know that's not true. But, all right, maybe I don't know this, so I say, all right, sine of minus x, I know that's minus sine of x. And I think, well, I'm trying to show these are the same, so I square both sides. So that would be minus sine of x squared equals sine squared of x. This is minus 1 squared times sine of x, sine squared x. And I end up showing that now I have sine squared of x equals sine squared of x. So I wrongly conclude that this is an identity. Well, where I went wrong is I did something that's not reversible. I squared both sides. If I reverse this, I don't necessarily get back to where I started from. So in general, you want to avoid performing operations on both sides. You want to stick with one side or the other. As we'll see a little later, you can follow both sides down, but you want to be careful that when you're doing this, your steps are reversible. All right. Any questions so far? Has anyone here not worked with identities before? I'm going to show you some examples, and I'll show you some of the tricks that come up a lot in trying to solve these. The only way you really learn how to do these is by practicing them. So there's a homework assignment. You should be pretty conscientious about it. If you can't figure something out, work with your friends, come in for office hours, but don't think this will just come to you in the exam. You really have to practice it a bit. They're like, after a while they're actually fun. They're like little puzzles. And you'll see that when you're doing them, often there's a step where you have to guess. You have to guess intelligently. And if you guess intelligently, you almost immediately get rewarded. The problem starts to look, oh, aha, that worked, and you can kind of see your way through the rest of it. Let's look at some examples, and I'll show you what I mean by some of these abstract things I'm stating here. let's start with cosine theta times secant theta minus cosine theta equals sine squared theta. Okay, I think I want to work on the left side here a little. But what would be a good first step? Anyone have any thoughts? Yes?
Change secant theta. Sorry. Can you
Change it to us.
the 1 over cosine?
Yeah, okay. So we have cosine theta times 1 over cosine theta minus cosine theta. Okay. Looks like a real good start, doesn't it? What might I do next to the left side? Distribute, yeah, okay. Cosine theta over cosine theta minus cosine squared theta. All right. Cosine theta over cosine theta is just 1, right? Whenever I see cosines and 1s and sines squared, cosine squared and sine 1s, I start to think about my trig identities, and whoa, look at that. I can substitute 1 minus cosine squared for sine squared. And that's exactly where I want to go. So this is pretty easy, right? Convert sines and cosines, distribute, simplify, and you're right there. Again, note that the steps are reversible. So while this complex expression equals sine squared is going to equal this. Right. This next example, it's not quite as straightforward. Requires a little more intuition or guesswork. But we're going to look at 2 tangent x secant x is going to equal 1 over 1 minus sine of x minus 1 over 1 plus sine of x. Okay. I could convert this to sines and cosines. That's sine over cosine times 1 over cosine, 2 sine over cosine squared. It doesn't really help me here, does it? It doesn't really tell me where I want to go. But this side, on the other hand, it's 2 fractions. And often it's a good idea when you have fractions to put them over a common denominator. Right? So let's try that here. The common denominator will be what? What's my common denominator? Yes?
1 minus sine squared x.
Yes, but you skipped a step that some people might not see, right? 1 minus sine x over 1 plus sine x, right? Well, okay. So this side I have to multiply by 1 plus sine x. And this side I have to multiply by 1 minus sine x. Look at this and I There's something about this that looks familiar, about this denominator. It looks an awful lot like a minus b times a plus b, which is a pattern I know. Right? What's a minus b times a plus b? If you don't know this, you're in trouble. Come get help. Right? This is, of course, a squared minus b squared, right? So that tells me 1 minus sine of x times 1 plus sine of x. Oh, this is wonderful. That's going to be 1 minus sine squared x, which, well, I know that's going to come in handy here. Right? All right, what do we have on top? We've got 1 minus 1. That goes away. Sine of x minus a minus sine of x. That's 2 sine of x. So this is going to become 2 sine of x over cosine squared x. At this point, it might be a good idea to take a look at where I want to go. Okay. I want to get this back to 2 tangent times secant. I like the fact there's a 2 here. That seems to be in the right place. Tangent, that's sine over cosine. 2 sine of x over cosine of x, and what's left? Times 1 over cosine of x. Just what I want. 2 times tangent of x times secant of x. So again, I think it's worth noting, there's a pattern here, right? 1 over 1 minus something, minus 1 over 1 plus something. My denominator, my common denominator is going to drop out something from one of the Pythagorean identities, and that's going to take me all the way over to where I want to be. All right. That's a nice thing to know, right? To have 1 minus a sign in the denominator, you can get rid of that. 1 plus a sign in the denominator. That's going to come in really handy in the next problem. I want to show cosine of x over 1 minus sine of x equals secant of x plus tangent of x. Now, a real obvious thing to do here, since we've already got sines and cosines over here, you might want to check out this side and say, well, what happens if we convert this? Get 1 over cosine of x plus sine of x over cosine of x. End up with 1 plus sine of x over cosine of x. Now we have to scratch our heads. How are we going to get that over here? That doesn't look that easy. So maybe that wasn't the best route. I mean, maybe we'll use that information, but all right. So here we have cosine of x over 1 minus sine of x. We could try something. We could try what we did on the last problem. We could multiply the denominator by 1 plus sine of x. So I have cosine of x over 1 minus sine of x. But I can't just do that. I need to multiply by 1. So this becomes 1 plus sine of x over sine of x. And the top will get cosine of x plus sine of x, cosine of x. On the bottom, we already know where we're going. This is going to be 1 minus sine squared x. It's just going to be cosine squared of x. Having made that leap, this is what we wanted to multiply this by. It's like suddenly now we should see that things are starting to fall into place. Because we have a factor of cosine in each of these terms. We can just eliminate that, right? I mean, this is cosine of x times 1 plus sine of x. And this is cosine of x times cosine of x. But this factor of 1 can just be canceled. That leaves us with, let's now separate this 1 over cosine of x plus sine of x over cosine of x. And now we're really close. This is secant of x plus tangent of x, which is again just where we want it to go. Usually there's just one crucial step you have to make, one kind of leap of faith, where you try something, and sometimes you will choose the wrong thing, and you just have to say, okay, that didn't work out. Start over, try something else. All right, any questions so far? Again, we'll get some practice on the homework on this, and feel free to come in and questions in class on any of the problems that seem overly difficult. Okay, there's one more aspect of this I want to show you. I mentioned this before. Let's take a look at an example. 1 plus cosine of x over cosine of x, and tangent squared x over secant x minus 1. You could try and find your way from here to there, or vice versa. But sometimes it's not always obvious how to get from one to the other. But you could kind of follow each of these down. You could kind of work each side, see if you can get them to correspond. Now, what makes that valid is if I convert this to something which is equal to something over here, that reversing my steps I get back here, then I've done what I needed to do. So let me show you what I mean by that. On the left side here, I have 1 plus cosine of x over cosine of x. So I'm gonna convert that. That's 1 over cosine of x plus 1, or secant of x plus 1. It's tempting to convert this to sines and cosines. If you do that, it will work out. But there's a hint here that maybe we don't want to jump to sines and cosines. Maybe we can solve this with secants and tangents and cosecants or whatever. And it turns out that is going to work out much nicer. How are we going to do that? Well, let's try our trick. let's try our trick where, well, how do I want to go about this? How I want to go about this is I want to take a look over here, and I want to see that I can convert my tangent squared to secant squared minus 1. Okay? All right, that already tells me I'm on the right track. Because I know I can factor this, right? Secant x minus 1, or secant x plus 1, or secant x minus 1. And so my secant of x minus 1 is going to drop out. Ah, look at that. I've made the connection here. Because now these two are equal, right? You might have to state, well, I can get from 1 plus cosine of x over cosine of x to secant of x plus 1, and I can get from tangent squared x over secant x minus 1 to secant of x plus 1. And my steps are all reversible. So going from here to here or back is all kosher. So proof is valid and the identity is correct. All right, I think that's pretty much it. Have questions?